Imagine staring into the night sky, where countless stars sparkle like scattered diamonds, each one a silent witness to secrets so vast they dwarf human understanding. Out there in the infinite black, mysteries lurk that defy everything we think we know. Galaxies spin in perfect harmony, yet dark matter, an invisible force, holds them together like cosmic glue we can't see or touch. Black holes warp time itself, swallowing light without a trace, and beyond it all, whispers of ancient signals echo across the void, hinting at questions we've barely begun to ask. This isn't just space, it's the greatest unsolved puzzle of all time, and today, we're diving headfirst into its deepest enigmas. You've probably wondered, staring up at those distant lights, what's really out there? The truth, space isn't just empty or silent, it's alive with phenomena so strange they seem ripped from science fiction. Take neutron stars, city-sized corpses of dead suns, so dense a single teaspoon would weigh 1 billion tons. Or rogue planets wandering the cosmos alone, untethered to any star. And what about the eerie Great Attractor, a gravitational anomaly so powerful it's pulling entire galaxies toward it, like some unseen cosmic magnet? These aren't just curiosities, they're clues to a universe far wilder than we've dared to imagine. That's why we're counting down 25 of the most jaw-dropping mysteries the cosmos has to offer. From the phantom radiation of the cosmic microwave background to the spine-tingling possibility of parallel universes, each one will leave you questioning the very fabric of reality. Some of these puzzles might never be solved in our lifetimes, but that's what makes them thrilling, so buckle up. By the end of this journey, you won't just see the night sky differently. You'll feel it, that humbling, heart-pounding awe of standing on the edge of the unknown, peering into the void and wondering what peers back. Hidden deep in the cosmic shadows lies a force so immense, it's dragging entire galaxies toward it like a cosmic riptide, and we can't even see it clearly. Meet the Great Attractor, one of the universe's most baffling puzzles. Nestled about 250 million light-years away in the direction of the constellations Centaurus and Hydra, this mysterious gravitational heavyweight is pulling the Milky Way and thousands of other galaxies toward it at a staggering speed of over 14 million miles per hour. But here's the catch: our view of it is blocked by the thick dust and stars of our own galaxy's disk, leaving astronomers to piece together clues like detectives peering through a fogged-up window. What makes this enigma even stranger is the sheer scale of its influence. The Great Attractor isn't just tugging on a few nearby galaxies, it's warping the motion of everything in our cosmic neighborhood, from the local group to distant clusters millions of light-years away. Some scientists think it might be a colossal supercluster of galaxies, so dense that its gravity dominates the region. Others speculate it could be something even more exotic, a knot of dark energy, a flaw in the fabric of space-time, or a gateway to structures beyond our current understanding. Then there's the Shapley supercluster, lurking even farther away, which might be amplifying the pull. It's like the universe is playing a game of tug-of-war, with the Great Attractor and Shapley as opposing teams, and we're caught in the middle. The more we learn, the clearer it becomes. This isn't just a curiosity, it's a cosmic wake-up call, reminding us how much of the universe remains hidden, pulling strings we're only beginning to sense. If the Great Attractor plays tug-of-war with galaxies, dark matter is the unseen referee holding the entire game together, except we've never actually seen it. This ghostly substance makes up roughly 85% of the universe's mass, yet it refuses to interact with light, leaving scientists to track its shadowy presence through the cosmic wreckage it leaves behind. Picture a merry-go-round spinning so fast, the children clinging to it should be flung off, yet somehow, they stay glued in place. That's exactly what happens in galaxies. Stars on the outer edges orbit just as fast as those near the center, defying the laws of gravity as we know them. The only explanation, an invisible halo of dark matter, its gravity gripping those stars like an unseen hand. But how do you study something that doesn't emit, absorb, or reflect light? Astronomers turn to cosmic trickery, gravitational lensing. When light from distant galaxies bends around massive objects, it creates distorted, stretched images like funhouse mirrors. The kicker: these distortions often reveal far more mass than the visible matter alone can account for. Entire galaxy clusters act like magnifying glasses, warping space-time in ways that scream there's something else here. So what is this elusive substance? The top suspects sound like sci-fi creations. WIMP weakly interacting massive particles theorized to flit through Earth like ghosts, barely nudging ordinary matter. Then there are actions: hypothetical particles so light, trillions could pass through your fingernail every second without a trace. Yet despite decades of hunting in underground labs and particle colliders, detectors remain eerily silent. Some wonder if dark matter isn't particles at all but primordial black holes left over from the Big Bang. Others argue we've got gravity itself all wrong, that our equations need rewriting. The irony: dark matter's fingerprints are everywhere, holding galaxies together, sculpting the cosmic web, even shaping the universe's fate, yet it remains the ultimate cosmic hide-and-seek champion. Every null result deepens the mystery, forcing us to question not just what's out there, but how much we truly understand the rules of the game. Just when we thought dark matter was perplexing enough, the universe threw us an even stranger curveball: dark energy. This mysterious force isn't just lurking in the shadows, it's actively reshaping the cosmos on a scale so vast, it challenges everything we thought we knew about gravity and the fate of the universe. Picture a balloon inflating faster and faster, not because someone's blowing into it harder, but because the rubber itself is stretching with invisible energy. That's the eerie reality we're facing. The discovery came in the late 1990s, when astronomers studying distant supernova made a jaw-dropping realization. These exploding stars, used as cosmic measuring sticks, were fainter than expected, meaning they were farther away than the expanding universe should have allowed. The only explanation: the expansion wasn't just continuing, it was accelerating, as if some unseen force was pushing galaxies apart with ever-increasing strength. That force, dubbed dark energy, now makes up a staggering 68% of the universe's total energy. But what could possibly overpower gravity, the very glue that holds galaxies together? One leading theory points to the cosmological constant, a term Einstein once called his greatest blunder, representing energy woven into the fabric of space itself. Empty space, it turns out, might not be empty at all. Quantum fluctuations could generate tiny bursts of energy, and when you add up all that seething activity across the cosmos, you get a repulsive force strong enough to stretch spacetime. Then there's the phantom menace scenario. Some models suggest dark energy isn't just constant, it's growing stronger over time. If that's true, the universe could face a catastrophic end known as the Big Rip. Imagine dark energy's push becoming so dominant that it overpowers every force in nature, tearing apart galaxies, then solar systems, then stars, and finally atoms themselves, leaving the cosmos as a cold, empty void. Yet for all its terrifying potential, dark energy remains almost as enigmatic as when it was first discovered. Is it truly constant, or does it evolve? Could it someday reverse, collapsing the universe in a big crunch? With experiments like the Dark Energy Survey and the upcoming Euclid Space Telescope, we're inching closer to answers, but for now, the universe's greatest game of tug-of-war continues, with dark energy as the ultimate wild card. The universe is unimaginably vast: trillions of stars, countless planets, and yet, silence, no signals, no alien megastructures, no cosmic chatter. This eerie absence is the heart of the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody? If the cosmos is so teeming with potential for life, why does it feel like we're the only ones here?" The answers we've come up with are as unsettling as they are fascinating. take the Great Filter theory, a hypothetical obstacle so extreme it prevents life from reaching interstellar levels. The terrifying possibility, the filter might still lie ahead of us. Maybe civilizations routinely wipe themselves out through war, climate collapse, or rogue AI before they can spread beyond their homeworlds. If that's true, humanity's greatest challenges could still be coming. On the flip side, the filter might be behind us. Perhaps the leap from simple chemistry to complex life is astronomically rare, and Earth just won the ultimate cosmic lottery. Then there's the zoo hypothesis, which suggests advanced civilizations are out there but deliberately hiding, observing us like animals in a galactic nature preserve. It sounds like sci-fi, but think about it, would we shout into the void if we discovered a planet of intelligent dinosaurs, or would we watch quietly, avoiding contamination? Others argue Earth itself is the anomaly, the rare Earth theory. Maybe habitable planets need not just the right distance from their star, but a perfect mix of plate tectonics, a large stabilizing moon, and a magnetic shield against radiation. Toss in the sheer timing, our universe is young, and we might simply be early to the party, but the darkest answer, silence, might be the norm. Civilizations could rise, blink out, and vanish without ever crossing paths in the cosmic timeline. Space is big, time is vaster, and the odds of overlapping might be cruelly slim. So when you look up at the stars tonight, remember the emptiness isn't just space. It's a question waiting. One moment the cosmos is silent, the next a blast of radio waves brighter than entire galaxies erupts, then vanishes in less time than it takes to blink. These are fast radio bursts, or FRB, some of the universe's most electrifying enigmas. First detected in 2007, these millisecond flashes pack the energy of 500 million suns, yet their origins remain shrouded in cosmic guesswork. Imagine hearing a thunderclap in broad daylight with no storm in sight. That's the level of confusion FRBs spark among astronomers. The mystery deepens with their unpredictability. Some burst once and never repeat, like cosmic one-hit wonders. Others fire off regular pulses, ticking like celestial clocks. One, dubbed FRB 121102, repeats every 157 days, as if something out there is following a schedule we can't comprehend. The leading suspect, magnetars, neutron stars with magnetic fields so intense, they could strip the data from a credit card halfway across the Milky Way. When these hypercharged corpses crack under pressure, they might unleash eruptions powerful enough to explain FRBs, but not all clues point to natural causes. The wildcard theory, advanced alien civilizations. Some scientists speculate these bursts could be propulsion beams from interstellar light sails. Think cosmic lighthouses guiding ships across galaxies. While the odds are slim, projects like the Breakthrough Listen initiative don't dismiss the possibility, scanning FRBs for encoded patterns that might betray artificial origins. Enter CHIME, the Canadian Hydrogen Intensity Mapping Experiment. This sprawling radio telescope in British Columbia acts like a cosmic net, snagging dozens of FRBs monthly. By mapping their frequencies and pinpointing host galaxies billions of light-years away, CHIME is slowly unraveling their secrets. One breakthrough came in 2020, when an FRB was traced to a spiral galaxy, surprisingly like our own, hinting these explosions might happen everywhere, under conditions we've yet to decode. The real thrill, FRBs aren't just cosmic curiosities, they're intergalactic messengers. As these waves traverse the universe, they interact with the sparse plasma between galaxies, carrying encoded maps of the cosmos's hidden structure. Decipher them, and we might finally weigh the universe's missing matter or even crack the code of dark energy. Until then, every burst is a tantalizing clue, and a reminder that the universe loves to keep us guessing. On the night of August 15, 1977, a radio telescope in Ohio picked up something that would haunt astronomers for decades, a 72-second burst of radio waves so intense, the scientist monitoring the data circled it in red ink and scribbled "Wow." Next to it, that single word gave the WOW signal its name, and almost 50 years later, it remains the closest we've ever come to hearing what might be an alien hello. What made this signal special wasn't just its strength 30 times louder than the cosmic background noise, but its frequency. It hit exactly 142 MHz, a quiet spot in the radio spectrum where hydrogen, the universe's most abundant element, naturally emits energy. It's like tuning a walkie-talkie to a dead channel and suddenly hearing a voice say your name. For that brief window, the signal matched what scientists predicted an interstellar beacon might sound like: narrowband, powerful, and seemingly artificial. The real mystery: it never happened again. Despite countless searches by telescopes from Arecibo to the Allen Telescope Array, the WOW signal remains a one-time event. Some argue it was a natural phenomenon, a comet's hydrogen cloud passing through the telescope's view, or a bizarre cosmic maser amplifying radio waves. The problem: no known comet was in that patch of sky that night, and natural radio bursts rarely mimic such a perfect, artificial-looking frequency. Then there's the chilling possibility it was artificial. If it came from an extraterrestrial transmitter, the signal's brevity suggests it wasn't meant for us. Maybe it was a fleeting radar pulse from a distant civilization, or a cosmic lighthouse sweeping past Earth by chance. The biggest roadblock: without a repeat signal, we can't triangulate its origin. It could have come from anywhere within the constellation Sagittarius, a region packed with hundreds of millions of stars. The WOW signal lingers like a cosmic prank, taunting us with its ambiguity. Was it a fluke of nature, or the universe whispering just loud enough to make us wonder? Either way, it's a stark reminder: in the search for extraterrestrial intelligence, patience isn't just a virtue, it's a necessity, because sometimes the universe offers a single, tantalizing clue, and then goes silent. Some stars flicker like candle flames in the wind, but then there's Tabby's star, flickering like a light bulb with a cosmic short circuit, officially named KZ8462852. This unassuming dot in the constellation Cygnus behaves like nothing else in the known universe. First flagged by astronomer Tabby in 2015, its light patterns are so erratic, they sparked headlines screaming "alien megastructure" and ignited one of modern astronomy's greatest debates. The anomalies start with its dips. Unlike regular exoplanet transits, where a planet blocks a star's light in predictable, symmetrical curves, Tabby's star dims chaotically, sometimes by a staggering 22%. Imagine holding your hand over a flashlight, except your fingers are made of invisible, shape-shifting patches that vanish and reappear at random. Early observations from the Kepler Space Telescope revealed clusters of bizarre, jagged dips spanning days or weeks, followed by long periods of eerie calm. Then came the real shocker. Archival data showed the star's overall brightness had dropped by 14% over the past century. Stars don't just fade like aging light bulbs, especially not middle-aged ones like this. So what's casting this cosmic shadow? Enter the wildest theory first: the Dyson swarm. Physicist Freeman Dyson once speculated that advanced civilizations might build vast energy-harvesting structures around stars. Think solar panels on a galactic scale. Could Tabby's star be partially wrapped in such a megastructure? Its irregular dimming caused by rotating arrays or construction projects, the idea wasn't entirely dismissed. Even serious astronomers admitted it was a remote possibility worth investigating. But as tantalizing as aliens are, Occam's razor prefers dust. Follow-up studies, especially those analyzing infrared light, pointed to clouds of fine particles, likely debris from comets, asteroids, or even a shattered planet drifting in uneven swarms around the star. Yet the plot thickens. Some scientists argue the dust explanation doesn't fully account for the star's century-long dimming or the extreme depth of certain dips. Others propose a more exotic culprit, a Trojan cloud, a gravitationally trapped band of debris akin to the asteroids that orbit ahead of and behind Jupiter. There's even a theory involving a massive ringed planet with a swarm of moonlets, each casting intricate shadows as they pass. What makes Tabby's star so compelling isn't just the mystery, it's the way it forces us to rethink what's possible. Most stars follow predictable rhythms, their lives governed by well-understood physics, but this one, it's a cosmic rebel, flickering on its own terms. Every new observation, whether from ground-based telescopes or citizen scientists scanning old photographic plates, adds another piece to the puzzle, and while the answer may turn out to be dust rather than Dyson spheres, the real lesson is humbling. The universe is stranger than our boldest guesses, and sometimes all it takes is one unruly star to remind us how much we have left to learn. Most of the universe looks like a crowded metropolis, galaxies packed together in glowing superclusters. But the Boötes Void is different. It's the cosmic equivalent of a ghost town, a vast, almost empty sphere stretching 330 million light-years across. If you dropped our Milky Way in there, the nearest neighbor galaxy would be so far away, its light would take millions of years just to reach us. That's not just unusual, it's statistically bizarre, like finding a desert the size of a continent where a rainforest should be. Discovered in the 1980s by astronomer Robert Kirshner, the void's emptiness defies expectations. Normally, even the sparsest regions of space still have a few dozen galaxies sprinkled throughout. But the Boötes Void, it's home to maybe 60 galaxies, at most less than 10% of what standard models predict. The handful of galaxies that do linger there are huddled together like survivors in an endless wasteland, leaving the rest of the space around them unnervingly dark. So how does a void this massive even exist? One theory points to cosmic inflation, the rapid expansion of the universe just after the Big Bang. Tiny quantum fluctuations during that period could have stretched into enormous bubbles of nothingness, leaving behind voids like this one. But even that doesn't quite explain why Boötes is so empty. Some researchers wonder if something more exotic is at play, like a collision with a parallel universe during inflation, leaving behind a scar in our cosmos. Then there's the unsettling possibility that the void isn't empty at all. What if it's packed with dark matter so dense it stifled galaxy formation? Or worse, what if a super-advanced civilization somehow cleared the region, turning it into a cosmic dead zone? The truth is, we just don't know. Every explanation feels like grasping at cosmic straws. The Boötes Void forces us to confront a humbling truth: the universe doesn't always play by the rules we've written for it. It carves out mysteries on scales we can barely comprehend, leaving us to piece together clues in the dark. And sometimes the most profound question isn't what's out there, it's why is there so much nothing? Space seems smooth, like an endless, unbroken sheet of glass until you zoom in closer than the width of an atom. Then the rules break down. At scales 100 billion times smaller than a proton, the universe might be churning with something called quantum foam, a seething, chaotic froth where spacetime itself loses all meaning. Picture an ocean during a storm. From a distance, the surface looks flat, but up close, waves crash, bubbles form and pop, and nothing stays solid for more than an instant. That's the realm of quantum foam, where spacetime isn't just warped, it's constantly tearing apart and stitching itself back together in a dance of creation and destruction. This frenzy isn't just theoretical. Black holes force us to confront it. When matter falls into one, what happens to the information it carried? According to quantum mechanics, information can't be destroyed, it must be preserved, scrambled, or hidden. But general relativity says black holes erase it forever. This clashes the black hole information paradox, and quantum foam might hold the key. Some physicists suggest that spacetime's frothy nature at microscopic scales could encode information in ways we can't yet detect, like cosmic graffiti etched into the fabric of reality itself. The real twist: quantum foam could rewrite gravity. Einstein's theory works flawlessly for planets and galaxies, but it ignores the tiny, turbulent world beneath. If spacetime is foamy, gravity might emerge from it like temperature emerges from the motion of atoms, a side effect of something far more fundamental. Theories like loop quantum gravity and string theory attempt to bridge this gap, proposing that spacetime isn't continuous but built from discrete, indivisible chunks, like pixels on a screen. Testing these ideas isn't just a challenge, it's a race against the limits of technology. Some experiments hunt for spacetime's graininess by studying ultra-high-energy cosmic rays. If spacetime is foamy, these particles should stumble on its bumps, slowing down slightly over vast distances. Others look for faint echoes in gravitational waves, ripples that might carry imprints of quantum foam's turbulence. What's at stake isn't just a deeper understanding of black holes or gravity. Quantum foam could redefine reality itself. Is spacetime the stage, or is it another actor in the cosmic play? Every unanswered question about it whispers the same thrilling possibility. We're standing at the edge of a revolution in physics, one that might reveal the universe as something far stranger than we ever dreamed. Black holes were supposed to be the universe's ultimate one-way streets, places where matter, light, and information vanish forever. But in the 1970s, Stephen Hawking made a discovery that turned this idea on its head. He showed that black holes aren't completely black, they leak. Tiny particles, now called Hawking radiation, slowly bleed energy away, causing the black hole to shrink and eventually evaporate. This revelation was groundbreaking, but it came with a terrifying catch. According to Hawking's math, all the information about what fell into the black hole would be lost forever, scrambled beyond recovery as the hole faded to nothing. Here's the problem that violates one of quantum mechanics' most sacred laws: information can't just disappear. Whether it's a book burning or a star collapsing, the universe always preserves the underlying data, like a cosmic backup drive. You might not be able to read it easily, but in principle it's still there. Hawking's idea suggested black holes were cosmic shredders, permanently erasing the universe's ledger. Physicists recoiled. Einstein's general relativity said black holes destroy information. Quantum mechanics said they couldn't. Something had to give. Enter the firewall paradox. In 2012, a group of physicists proposed a brutal solution. The event horizon, the point of no return, might not be the smooth gateway we thought. Instead, it could be a raging wall of high-energy particles, incinerating anything that crosses. Think of it like walking through what you thought was a curtain, only to find it's actually a sheet of flame. This would preserve information by destroying the infalling matter before it ever reached the singularity, but it came with its own glaring issue. An observer falling into a black hole shouldn't notice anything unusual at the horizon. That's baked into Einstein's equations. Firewalls would mean relativity breaks down catastrophically at the very edge of a black hole. Then there's the holographic principle, perhaps the most mind-bending fix of all. It suggests that all the information sucked into a black hole isn't lost, it's smeared across its surface like a cosmic etch-a-sketch, the three-dimensional stuff inside. Just a projection, like a movie playing on a screen. In this view, black holes obey quantum rules by encoding everything they swallow in 2 dimensions, even as the original objects vanish in 3. It's as if you burned a dictionary, but all its words rearrange themselves into a perfect, invisible barcode on the ashes. The stakes couldn't be higher. If information can escape black holes, it might be through mechanisms we've yet to imagine: wormholes, hidden dimensions, or quantum entanglement weirder than anything in sci-fi. If it can't, we might need to rewrite physics from the ground up. Every new theory, from string theory's fuzzballs to loop quantum gravity's spacetime stitches, is a desperate attempt to solve this puzzle. Because in the end, the black hole information paradox isn't just about what happens to doomed stars, it's about whether the universe plays by rules we can never fully understand, or if, deep in the dark, it's rewriting them as it goes. The cosmic microwave background, the afterglow of the Big Bang, should be the universe's most democratic feature, a nearly uniform veil of radiation stretching in all directions. But in 2005, astronomers stumbled onto something that made no sense. The CMB's subtle temperature fluctuations, those tiny wrinkles in spacetime, weren't randomly scattered. They were aligned bizarrely with the plane of our solar system. Scientists called it the axis of evil, partly as a dark joke, partly because it threatened to upend one of cosmology's sacred principles: the universe, on large scales, should have no preferred direction. This isn't just a quirk of statistics. The alignment defies the Copernican principle, the idea that Earth holds no special place in the cosmos. If the CMB's hottest and coldest spots line up with our solar system's ecliptic, it's like discovering that every painting in a gallery was hung to face your seat. The odds of this happening by chance, less than 1 in 1,000. Some researchers argue it's a fluke, an artifact of measurement errors or galactic dust muddying the data. But after multiple satellites from WMAP to Planck kept detecting the same eerie pattern, the anomaly refused to vanish. Then come the wilder theories. Could our solar system be caught in a cosmic wake, left by some primordial structure that warped spacetime on unimaginable scales? Or is this a fingerprint of a multiverse, where neighboring universes tug at ours like invisible magnets? The most unsettling possibility: the axis might hint that the universe isn't just lopsided, it's oriented in a way that somehow acknowledges our existence. Skeptics counter that human brains are pattern recognition machines, wired to see significance where none exists, yet the axis of evil lingers, a cosmic riddle that refuses to be explained away. Whether it's a shadow on our data or a crack in the foundation of modern cosmology, one thing's certain: the universe keeps finding ways to unsettle us, whispering that we might not be as insignificant as we thought. When the Pioneer 10 and Pioneer 11 spacecraft hurtled beyond the solar system, they carried humanity's hopes into the void, but they also carried a puzzle. By the 1990s, radio tracking revealed something odd. Both probes were slowing down just a fraction more than expected, as if an invisible hand were gently tugging them backward. This tiny discrepancy, a deceleration smaller than a snail's pace, became known as the Pioneer anomaly, and for decades, it haunted physicists like a ghost in the machinery of the cosmos. At first glance, the numbers seemed insignificant, a drift of about 300 miles over 25 years, but in the precise realm of orbital mechanics, where every millimeter counts, this was a glaring red flag. The probe's trajectories had been calculated down to the gravitational pull of every planet, the nudge of solar radiation, even the faint push of cosmic dust. Yet here they were, defying predictions with stubborn consistency. Some wondered if Newton's laws needed tweaking at interstellar distances. Others whispered about dark matter's gravitational whispers, or even undiscovered dimensions warping spacetime. Then came the eureka moment, or so it seemed. In 2012, a team of researchers proposed a mundane but elegant solution: heat. Pioneer's nuclear power sources emitted warmth, and that thermal radiation, bouncing unevenly off the spacecraft's asymmetrical bodies, could create just enough recoil to explain the anomaly. It was like a car idling in neutral. The engine's faint vibrations might inch it backward over time. When scientists painstakingly reconstructed Pioneer's heat emissions, the math finally aligned. Case closed, not quite, because here's the catch: while thermal recoil accounts for most of the anomaly, some measurements still show a whisper of discrepancy. Could there be another layer to this mystery? A few scientists speculate that our models of gravity itself might need refinement at extreme scales. Modified Newtonian dynamics, or a controversial alternative to dark matter, suggested that gravity behaves differently in the near emptiness of deep space. Others point to the Kuiper belt's unseen mass, or the gravitational echoes of long-dead stars. The Pioneer anomaly is a reminder that even the smallest cosmic hiccup can ripple into big questions. It's a tale of scientific humility, how a few unexplained millimeters forced us to recheck our equations, our assumptions, even our understanding of the universe's invisible rules. And while most agree the case is largely solved, that lingering uncertainty, that's where the real magic lies, because in the gaps of our knowledge, the universe always finds a way to surprise us. We think we know what the universe is made of: dark energy, dark matter, and a sprinkle of ordinary stuff like atoms and stars, but here's the catch: even that tiny fraction of normal matter isn't all accounted for. Half of it's missing, not hiding in black holes or tucked inside distant planets, but gone, vanishing into the cosmic ledger like a bank error nobody can explain. This is the missing baryon problem, and solving it means staring into the emptiest places in existence to find what's been right in front of us all along. Baryons, the protons and neutrons that make up everything from your coffee mug to Jupiter, should be easy to track. After all, they're the building blocks of visible reality. But when cosmologists tallied up all the ordinary matter created after the Big Bang, the numbers didn't add up. Galaxies, gas clouds, and interstellar dust account for barely half of what theory predicts. The rest, a cosmic shell game on an unimaginable scale. Enter the WIM, the warm, hot intergalactic medium. This elusive web of superheated gas, threaded between galaxies, is so tenuous it's practically invisible. Imagine steam rising from a cup of tea, except the cup is a billion light-years wide, and the steam is a million-degree plasma too faint to see directly. The WIM isn't just wispy, it's dark, absorbing and emitting light at wavelengths most telescopes can't detect. But when galaxies collide, their shock waves squeeze these filaments, making them glow faintly in X-rays and ultraviolet, brief cosmic flares hinting at the missing matter's hiding place. The hunt for the WIM is like tracking ghosts with a flashlight. Telescopes like ESA's XMM Newton and NASA Chandra scan the sky for X-ray whispers, while instruments like the Hubble Space Telescope use quasars' ultra-bright galactic cores as backlights. As quasar light travels through the WIM, specific wavelengths get absorbed, leaving fingerprints in the data. It's detective work on a galactic scale, piecing together clues from light that's traveled for billions of years. But the real breakthrough might come from something even stranger: fast radio bursts. These intense, millisecond-long radio signals from distant galaxies get subtly distorted as they pass through the WIM. By measuring how the bursts slow down, astronomers can map the WIM density, turning transient cosmic static into a baryon census. The stakes: if we find the missing matter, it confirms our models of cosmic evolution. If we don't, we might need to rethink how the universe structured itself after the Big Bang. Either way, the answer is out there, woven into the faint, shimmering threads of the cosmic web, waiting to be pulled into the light. The moon seems like a dead, dusty world: no volcanoes, no atmosphere, certainly no global magnetic field to shield it from solar winds. But pick up certain ancient lunar rocks, and they tell a different story. These silent witnesses carry traces of an impossible past, remnants of powerful magnetism, as if the moon once had a magnetic field rivaling Earth's. How could something so small, just 1% of Earth's mass, ever generate such a force? The answer might rewrite what we know about planetary cores and the secrets hidden beneath barren surfaces. Here's the puzzle. When Apollo astronauts brought back moon rocks, scientists expected them to be magnetically blank. Instead, some samples, especially those over 3 billion years old, were magnetized. Locked in their crystals were records of a field up to 100 times stronger than today's moon could ever produce. It's like finding a fossilized lightning bolt in a desert. The leading theory, a dynamo effect: Earth's magnetic field comes from our churning, molten outer core, where swirling currents of liquid iron generate magnetism like a cosmic generator. But the moon's core is tiny, barely 600 miles across. Even if it were molten once, simple math says it shouldn't have had the energy to sustain such a strong field for long. Enter the sleuthing. One clue lies in the Moon's early orbit. Billions of years ago, it sat much closer to Earth, and tidal forces, the same pull that creates ocean tides, might have stretched and heated the Moon's interior like kneading dough. This friction could have kept the core molten far longer than expected, fueling a temporary dynamo. Another idea points to colossal impacts. When asteroid strikes rocked the young Moon, the violence might have stirred the core violently enough to jumpstart magnetism, like shaking a snow globe. Then there's the wildcard precession. Picture a spinning top wobbling before it falls. The Moon's axis likely wobbled dramatically in its youth, causing the core and mantle to rotate at slightly different speeds. That shear could have churned the molten metal inside, creating a magnetic field as a byproduct. Recent computer simulations show this mechanical dynamo might explain the Moon's brief but intense magnetic heyday. But the plot thickens. Some rocks suggest the field didn't fade gradually, it flickered, surging and collapsing in fits and starts. That's left scientists wondering if the Moon's core didn't just cool evenly, but underwent spasms of activity, like a dying fire sparking one last flame. Each theory has holes. Tidal heating can't fully explain the field's strength. Impact-driven dynamos would need impossibly frequent strikes, and precession models struggle to account for the field's longevity. The real kicker: this isn't just about the Moon. If such a small body once had a magnetic field, other moons and asteroids might have too, places we'd never think to look for signs of ancient shielding. That changes the game for understanding where life could have taken root in our solar system. Magnetic fields protect atmospheres from being stripped by solar winds, and atmospheres shelter potential life. So the Moon's magnetic past isn't just a curiosity, it's a clue that even the quietest worlds might have once been vibrant, dynamic places, and that the universe loves to hide its greatest dramas in the unlikeliest corners. On October 19, 2017, astronomers spotted something that shattered all expectations: a visitor from another star system, tumbling past the Sun at breakneck speed. Named Oumuamua, Hawaiian for scout, this cosmic interloper wasn't just the first object we've seen from beyond our solar system. It was wrong in ways that still baffle scientists today. First, its shape. Most asteroids and comets are lumpy potatoes or jagged boulders, but Oumuamua was different. As it spun, its brightness varied wildly, 10 times more than any known solar system object, suggesting an extreme elongated form. Picture a pancake flipped end over end, or a cigar hundreds of feet long but maybe just 35 wide. Then came the real shock: its acceleration. Unlike ordinary comets, which speed up when sunlight vaporizes their ices in predictable bursts, Oumuamua didn't show any visible outgassing, no dusty tail, no coma, nothing. Yet something was pushing it ever so slightly off its expected path. The explanation split the scientific community. On one side, the comet camp argues Oumuamua was a cosmic iceberg, made of hydrogen or nitrogen so exotic that its outgassing left no trace. Harvard's Avi Loeb countered with a provocative alternative: what if it wasn't natural at all? His controversial hypothesis suggested Oumuamua's acceleration matched a light sail, a thin, artificial object pushed by starlight, perhaps debris from an alien civilization. The backlash was swift. Critics called it sensationalism, pointing out that nature excels at creating oddities we've never seen before, the truth we might never know. Oumuamua raced out of telescopic range before we could study it further, leaving behind a trail of questions. Was it a fragment of a Pluto-like world from another system? A shattered remnant of a rogue planet? Or something even stranger? The real lesson isn't just about one object, it's about how unprepared we are for the next interstellar visitor. Because if Oumuamua taught us anything, it's that the universe specializes in throwing curveballs, and the next one might be even harder to catch. Measuring the universe seems like it should be simple: track how fast galaxies move apart, crunch some numbers, and voila. But when the world's best telescopes deliver answers that flat out contradict each other, you know something's deeply wrong. That's the Hubble tension, a cosmic standoff so stubborn, it's making scientists question whether we've misunderstood the universe's very fabric. On one side, the Planck satellite's pristine measurements of the cosmic microwave background, the afterglow of the Big Bang. By studying subtle temperature ripples in this ancient light, Planck calculated the universe's expansion rate, the Hubble constant, at about 67 kilometers per second per megaparsec. That means for every additional megaparsec of distance, a staggering 3.26 million light-years, space itself stretches 67 kilometers faster every second. Solid physics, impeccable data. Then came the curveball. Teams using the Hubble Space Telescope and ground-based observatories watched pulsating stars and supernova in nearby galaxies, cosmic yardsticks whose distances and speeds we can measure directly. Their result 73, same units, wildly different number. At first everyone assumed someone made a mistake, but after decades of double-checking, the gap refused to close. We're not talking rounding errors here. The discrepancy is over 7%, enough to throw cosmic timelines into chaos. If the Hubble constant is higher, the universe might be younger than we thought. If it's lower, dark energy's influence could be stranger. So where's the glitch? One camp blames hidden systematic errors, tiny biases in how we measure supernova or CMB data. Maybe interstellar dust dims supernova unexpectedly, or our models of stellar physics are slightly off. Others think we're missing something fundamental. Could dark energy evolve over time, accelerating expansion faster than predicted? Might there be a shadowy, dark radiation component left over from the Big Bang, tweaking the early universe's expansion just enough to throw off Planck's numbers? Then there's the nuclear option, new physics. Some theorists propose modifications to Einstein's gravity, suggesting it weakens slightly on cosmic scales. Others flirt with early dark energy, a hypothetical force that briefly surged during the universe's first 300,000 years, altering the CMB's snapshot before vanishing without a trace. The most radical idea, we're seeing echoes of a collision with another universe during inflation, leaving scars in the expansion rate. Every new observation sharpens the mystery. The James Webb Space Telescope's ultra-precise infrared eyes recently confirmed Hubble's supernova measurements, deepening the rift. Upcoming projects like the Vera Rubin Observatory and ESA's Euclid mission will hunt for cracks in our models, scanning millions of galaxies for clues. One thing's certain, this isn't just about numbers on a screen. The Hubble tension is a battleground for cosmology's future, and right now, the universe is winning. Picture the universe not as a scatter of isolated galaxies, but as a colossal, intricate spiderweb, one woven from threads of dark matter and hot gas stretching hundreds of millions of light-years. This is the cosmic web, the hidden architecture of the cosmos, where galaxies are mere specks of dew clinging to its silken strands. For decades, astronomers suspected something bound the universe's structure together, but it wasn't until the Sloan Digital Sky Survey (SDSS) turned its telescope skyward that we began to see this ghostly skeleton in stunning detail. The filaments themselves are mind-bendingly vast, each one is a river of ionized gas, superheated to millions of degrees, flowing along corridors of invisible dark matter. Where these threads intersect, galaxies cluster like glittering cities at cosmic crossroads. The rest, a haunting emptiness, gigantic voids so devoid of matter, they could swallow our entire local group of galaxies without a trace. Mapping these filaments is like trying to trace the outline of a shadow. They don't emit light, but their fingerprints are everywhere. When light from distant quasars passes through them, certain wavelengths get absorbed, revealing the web's chemical makeup like a cosmic barcode. What's truly humbling is how much of this structure we've missed. Early galaxy surveys showed stars clustering in odd patterns, but it took supercomputer simulations to connect the dots. By modeling the gravitational dance of dark matter from the Big Bang to today, programs like the Millennium Simulation revealed something astonishing: the universe's matter didn't spread evenly. Instead, it collapsed into this intricate network, shaped by tiny quantum fluctuations in the newborn cosmos. Now, projects like SDSS Dark Energy Spectroscopic Instrument (DESI) are going further, capturing the spectra of millions of galaxies to reconstruct the web in 3 dimensions. The goal: to understand how dark energy stretches these filaments apart, and whether the web holds clues to the universe's ultimate fate. Because here's the spine-tingling truth: we're not just observers of this vast structure. We're part of it, tiny threads in a tapestry whose full pattern we've only begun to trace. Among the cosmic microwave background's subtle wrinkles, one anomaly stands out like a frostbite scar on the universe's oldest light, the Eridanus Supervoid. Stretching over a staggering billion light-years, this cosmic cold spot is so vast, it defies probability. Temperatures in its region dip lower than anywhere else in the CMB, as if a chunk of the early universe simply forgot to warm up. When astronomers first spotted it in 2004, the discovery sent shockwaves through cosmology. Was this a fluke of statistics, or a window into something far stranger lurking beyond the edge of our observable reality? At first glance, the void's explanation seems straightforward. Empty regions of space where galaxies and matter are scarce stretch light traveling through them, shifting its energy toward cooler wavelengths. It's called the integrated Sachs-Wolf effect, and it's like walking out of a heated building into winter air. The light loses energy crossing this cosmic wasteland. But here's the catch: the Eridanus Supervoid is too big and too cold. Simulations show that a void this massive should be vanishingly rare in our universe, less than a 1 in 50 chance of existing at all. That improbability fuels wilder theories. Some physicists argue the cold spot might be a bruise from a collision with another universe during cosmic inflation. In multiverse models, neighboring bubble universes could leave imprints on ours as they bump and separate, like soap bubbles merging in a sink. Others propose it's evidence of a cosmic defect, a tangled knot in spacetime's fabric left over from the Big Bang. Then there's the quantum entanglement explanation, suggesting the early universe's particles were linked across vast distances in ways we don't yet understand, leaving behind anomalies like this one. Not everyone's convinced. Skeptics point to the Keenan-Barger-Cowie void, a slightly smaller underdense region overlapping part of the cold spot, as a potential culprit. If confirmed, this near void could partially explain the temperature dip without invoking multiverses or new physics. But even then, the numbers don't fully add up. The cooling effect wouldn't account for the entire anomaly. The debate rages on, fueled by new data from telescopes like Planck and the Atacama Cosmology Telescope. Some observations suggest the cold spot might be surrounded by a mysterious ring of hotter plasma, adding yet another layer to the puzzle. Whether it's a statistical ghost or a crack in our cosmic model, the Eridanus Supervoid forces us to confront an unsettling truth. The universe might be hiding its biggest secrets in the places we least expect, the empty voids where nothing seems to happen at all. Most galaxies play by the rules swaddled in massive halos of dark matter, their gravity dominated by this invisible glue. Then there's NUC 1052DF2, the cosmic rebel that flips the script entirely. Discovered in 2018, this ultra-diffuse galaxy, a wispy, ghostly sprawl of stars, should be teeming with dark matter. Instead, studies revealed something shocking: it seems to have none. Not just a little less than expected, but a staggering deficit that defies everything we thought we knew about how galaxies form. The evidence comes from the stars themselves. By tracking their motions, astronomers can calculate the galaxy's total mass. In normal galaxies, stars orbit so fast that without dark matter's extra gravitational pull, they'd fly apart like a spinning merry-go-round with no bolts. But in DF2, the stars move sluggishly, as if there's nothing invisible holding them together. The numbers don't lie. This galaxy's mass matches its visible stars and gas almost perfectly. No dark matter required. Cue the cosmic detective work. One camp argues DF2 might be a victim of tidal stripping, a brutal gravitational mugging. If it wandered too close to a massive neighbor, like the elliptical galaxy NGC 1052, tidal forces could have ripped away its dark matter while leaving the stars relatively untouched. Picture a thief stealing the stuffing from a pillow but leaving the fabric intact. The problem? DF2 isn't showing the usual scars of such an encounter, like stretched out tidal tails or distorted shapes. Then there's the measurement debate. Some scientists question whether we're even seeing DF2 correctly. Its distance from Earth is tricky to pin down, get it wrong, and calculations about its mass and size could be off. Others suggest its weird globular clusters, unusually bright and sparse, might be skewing the data, but follow-up studies, including observations of a second dark matter-deficient galaxy, DF4, suggest this isn't a fluke. The universe might genuinely be building galaxies in ways we never anticipated. What if DF2 is a cosmic accident? One theory posits it formed from gas flung outward during a violent galactic collision, leaving it star-rich but dark matter poor. Or maybe it's the product of an entirely different process, one where gas cools so efficiently in the early universe that it bypasses dark matter's gravitational pull altogether. The implications are staggering. If galaxies can form without dark matter, it challenges the very foundation of modern cosmology that dark matter isn't just a component of the universe, but its essential scaffold. The real twist: DF2 might not be alone. Since its discovery, other oddball galaxies with suspiciously low dark matter have emerged, hinting at a whole population we've overlooked. Whether they are cosmic outliers or the tip of an invisible iceberg, one thing's clear: the universe loves to break its own rules, and every time it does, we're left scrambling to rewrite the textbooks. In the world of particle physics, we're used to things making sense: quarks, electrons, photons, all neatly organized in the standard model like ingredients in a cosmic recipe. But what if there's something else out there, something that doesn't play by any of the usual rules? Enter the unparticle hypothesis, one of the strangest and most speculative ideas in modern physics. This isn't just about discovering a new particle, it's about rewriting the playbook entirely. The idea was first proposed in 2007 by physicist Howard Georgi, and it's as mind-bending as it sounds. Unparticles wouldn't behave like ordinary matter. They wouldn't have a definite mass or energy. Instead, they'd exist in a sort of quantum limbo, acting like a smear across space-time rather than a discrete object. Picture trying to weigh a cloud, not the droplets within it, but the cloud itself as a single, shifting entity. That's the eerie quality of unparticles. They defy the very definition of what a particle should be. What makes this more than just a wild thought experiment is where these unparticles might be hiding. Some theorists suggest they could be lurking in the shadows of dark matter, or even fueling dark energy's mysterious push. If dark matter isn't made of WIMP or actions but of unparticles, it would explain why our detectors keep coming up empty. How do you catch something that doesn't behave like anything else in the universe? Then there's the space-time angle. Unparticles could interact so weakly with ordinary matter that they're practically ghosts, yet their presence might still warp the fabric of reality in subtle ways. Imagine a universe where gravity isn't the only force sculpting the cosmos. Unparticles could be tugging at galaxies, tweaking the expansion of space, or even creating faint ripples in the cosmic microwave background. Of course, the big question is, how do we find them? Experiments at the Large Hadron Collider and other high-energy facilities are hunting for anomalies that might hint at unparticle behavior. Others are looking for tiny deviations in gravitational waves or the decay rates of known particles, but the real challenge is that unparticles, if they exist, might leave fingerprints too faint for current technology to spot. The unparticle hypothesis forces us to confront an exhilarating possibility. that the universe is far weirder than our models can currently describe. Whether it's a dead end or a revolution in waiting, one thing certain: physics has never been shy about venturing into the unknown, and sometimes the most radical ideas are the ones that unlock the deepest truths. Out beyond Neptune, where sunlight dwindles to a faint glimmer, lies a ring of icy leftovers from the solar system's birth, the Kuiper belt. This frozen frontier should teem with objects, growing sparser the farther you go. But something bizarre happens around 50 astronomical units out. The belt doesn't just thin out, it plummets, as if someone drew a cosmic boundary line, and everything beyond it simply vanished. Astronomers call this the Kuiper cliff, and its existence threatened to upend our understanding of how the solar system's edges took shape. The numbers don't add up. Based on models of the early solar system's protoplanetary disk, we'd expect a gradual decline in objects, like a beach sloping gently into the ocean. Instead, it's more like stepping off a cliff. One moment you're surrounded by icy rocks, the next, nothing but empty space. Even stranger, the drop-off happens too fast to be explained by natural erosion or collisions. So what's sweeping this region clean? Enter the leading suspect, Planet 9. This hypothetical super-Earth, lurking hundreds of away, could be hurting Kuiper belt objects with its gravity, sculpting their orbits like an invisible shepherd. Some simulations show a massive planet in a distant, elongated orbit would fling smaller bodies outward while clearing others entirely, leaving behind a sharp edge. The catch: no one's actually seen Planet 9 yet. Its existence is inferred from odd orbital alignments among a handful of extreme trans-Neptunian objects, clues subtle enough to be cosmic coincidences. But there's another, darker possibility. What if the cliff isn't caused by a hidden planet at all, but by the violent conditions of the solar system's infancy? In the chaos of the early solar system, Jupiter's migration might have flung debris outward before retreating inward, leaving behind a truncated disk. Or perhaps the young sun's stellar neighbors, other newborn stars in its birth cluster, stripped away the outer layers of our Kuiper belt billions of years ago. Imagine a group of toddlers playing in a sandbox, each kicking sand into the other's space, except the sand is primordial ice, and the toddlers are stars. Then there's the wild card, observational bias. Could the Kuiper cliff just be an illusion, a gap created because we haven't looked hard enough? Surveys like the Outer Solar System Origins project are scanning deeper, but the farther out you go, the fainter objects become. It's like searching for fireflies at the edge of a flashlight's beam. The ones farthest away might be invisible to our instruments. The Kuiper cliff isn't just a curiosity. It's a fossil record of the solar system's most turbulent era, a time when planets jostled for position and the outer reaches were reshaped by forces we're only beginning to grasp. Whether the culprit is a hidden world, ancient stellar bullies, or our own blind spots, one thing's certain: the edge of the solar system holds secrets we've barely begun to uncover. And until we solve this mystery, every icy rock beyond 50O is a silent witness to something extraordinary. We just don't know what yet. Mars should be a dead world: no forests, no swamps, no belching volcanoes. So when NASA Curiosity rover started sniffing methane in the thin Martian air, scientists didn't just take notice, they scrambled, because methane is a gas that, on Earth, is practically screaming life, belched by everything from cows to microbes. But Mars isn't Earth, and this methane isn't behaving like anything we've seen before. Curiosity's readings are maddeningly inconsistent. Some days the rover detects faint whiffs, trace amounts, barely a few parts per billion. Then, without warning, the levels spike. In June 2019, Curiosity hit the jackpot, a methane concentration 20 times higher than baseline, vanishing almost as fast as it appeared. It's like walking through a desert and suddenly catching the scent of fresh bread, only for the wind to snatch it away before you can find the bakery. So where's it coming from? The debate splits into two camps. geology versus biology. On one side, serpentinization, a process where water reacts with certain rocks, like olivine, to produce methane. Mars has plenty of these minerals, and if groundwater still seeps through them deep below the surface, the reaction could explain the gas. Another possibility is clathrate methane ice trapped in the soil, released when temperature or pressure shifts. Then there's the elephant in the room, microbes. On Earth, most methane comes from living things, especially anaerobic bacteria that thrive without oxygen. If Mars ever had, or still has subsurface life, even in isolated pockets, it could be producing methane as a byproduct. The spikes suggest localized, intermittent sources, like tiny geysers of gas bubbling up from underground reservoirs. Enter Perseverance. While Curiosity's instruments detect methane, they can't pinpoint its origin. Perseverance's mission includes a crucial upgrade, a spectrometer fine-tuned to analyze methane's carbon isotopes. Life on Earth prefers lighter carbon isotopes, leaving a distinct fingerprint. If Martian methane shows that same bias, it's not proof, but it's a smoking gun. The real puzzle isn't just the methane's presence, but its fleeting nature. Sunlight and chemical reactions should destroy methane within a few hundred years, meaning whatever's producing it is either still active, or the gas is being released from some ancient, sealed reservoir. Either scenario rewrites Mars' story. One thing's certain, the red planet is playing a cosmic game of hide and seek, and we're just starting to learn the rules. Saturn isn't just a planet, it's a celestial magician, dazzling us with rings so pristine they seem painted on, but its greatest trick isn't in the sky, it's at the top. Nestled around Saturn's north pole is a structure so geometrically perfect, it looks like it was carved by aliens, a colossal hexagon, wider than 2 Earths, with winds screaming at 320 miles per hour. This six-sided jet stream isn't just a fleeting cloud pattern, it's been raging for at least 4 decades, maybe longer, defying every expectation of how planetary atmospheres behave. The first hints came from Voyager's flybys in the 1980s, but it wasn't until Cassini arrived in 2004 that we grasped the hexagon's true strangeness. Unlike Earth's messy, meandering jet streams, Saturn's hexagon is unnervingly precise. Its 6 near-identical sides stretching over 18,000 miles, each corner locked in place like the bolts of a cosmic nut. Even more bizarre, the structure barely wobbles, maintaining its shape as it rotates with Saturn's atmosphere, as if etched into the planet itself. So how does a gas giant produce something so rigidly geometric? The leading theory points to shear forces, layers of atmosphere moving at different speeds, creating turbulence that somehow locks into a stable hexagon. Picture stirring a cup of tea with a spoon. If you move the spoon just right, swirling eddies can form repeating patterns. On Saturn, these fluid dynamics might be playing out on a planetary scale, with the hexagon acting like a standing wave, frozen in place by the planet's rotation. Lab experiments back this up. Researchers at Oxford recreated miniature versions using spinning water tanks, adding fluorescent dye to track flow patterns. When the fluid reached certain speeds, polygons including hexagons emerged spontaneously. The key ingredient: gradients in wind speed, like those on Saturn, where jet streams shear against slower-moving air. But here's the catch: while these experiments produce polygons, none have matched the stability or scale of Saturn's monster. Then there's the wild card: deep-seated turbulence. Some models suggest the hexagon isn't just a surface feature but a shadow of deeper chaos, like foam bubbling up from Saturn's churning interior. Others wonder if the planet's magnetic field, interacting with charged particles in the atmosphere, plays a role, adding electromagnetic spice to an already volatile mix. The hexagon's persistence is what truly baffles scientists. Earth's weather systems change by the hour, yet Saturn's crowning jewel has outlasted entire space missions. Is it fed by hidden energy sources deep within the planet, or is it a rare equilibrium? a cosmic coincidence of wind, rotation, and temperature that could vanish as suddenly as it appeared. Every new observation peels back another layer of mystery, because in the end, Saturn's hexagon isn't just a curiosity, it's a reminder that even the most familiar planets still hold secrets written in the language of storms. The universe has a beginning, a fiery burst from nothingness we call the Big Bang, but what about its end? The answer isn't written in the stars, it's hidden in the invisible tug of war between dark energy, gravity, and the very fabric of space-time. Will the cosmos fade into icy silence, collapse in a fiery reversal, or cycle endlessly like a phoenix reborn? The possibilities are as breathtaking as they are terrifying, each one rewriting what it means for time itself to have an expiration date. Let's start with the most haunting scenario: heat death. Picture a universe so stretched thin, every star has burned out, every black hole evaporated, and every particle of matter decays into faint, useless radiation. Space, now cold and empty, continues expanding at an ever-accelerating pace, driven by dark energy's relentless push. Galaxies beyond our local group vanish over the cosmic horizon, their light stretched beyond detection. Time, stripped of meaningful change, becomes a meaningless concept. This isn't just an end, it's the slow erasure of existence itself, a whisper fading into infinite silence. Calculations suggest this fate is likely if dark energy remains constant, but what if it isn't? That's where the big crunch comes in. If dark energy weakens over time, or reverses into an attractive force, gravity could finally win the cosmic war. Galaxies would stop racing apart and begin falling back toward each other, space contracts, temperatures soar, and the universe collapses into a singularity, mirroring the Big Bang in reverse. Some theories even propose this singularity could trigger another Big Bang, birthing a new universe in an endless cycle. It's a poetic idea, but there's a catch. Current observations of accelerating expansion suggest dark energy isn't loosening its grip. Unless it's hiding a dramatic phase shift, the crunch might remain science fiction. Then there's the wild card, the Big Rip. If dark energy grows stronger over time, its repulsive force could eventually overpower every binding force in nature. First, galaxy clusters tear apart, then individual galaxies, stars are ripped from their orbits, planets shredded, atoms themselves split asunder. In this nightmare scenario, the universe doesn't just end, it's violently disassembled piece by piece. The timeline, some models estimate as little as 22 billion years from now. That might sound distant, but on cosmic scales, it's a blink. But what if the universe has no end at all? Cyclic models propose an endless loop of universes, each one expanding, contracting, and rebounding like a cosmic lung. String theory's ekpyrotic universe suggests colliding branes, higher dimensional membranes could reignite creation over and over. The appeal: no true beginning or end, just an infinite dance of destruction and renewal. Yet even here, mysteries linger. What triggers each cycle? Why does entropy not accumulate, rendering each iteration colder and emptier? The real twist: we might be asking the wrong question. Time itself could be an illusion, a human construct that breaks down at cosmic scales. In a multiverse or holographic reality, the end might be as meaningless as asking what's north of the North Pole. Whatever the answer, one thing's clear: the universe's fate isn't just about physics, it's about the stories we tell to make sense of infinity and our fleeting place within it. What if everything around you, the stars, the air, even your own thoughts, weren't real? Not in the abstract sense, but in the most literal way possible, an artificial simulation, meticulously coded by some advanced civilization running experiments on an unfathomable scale. This is the simulation hypothesis, a modern twist on an ancient philosophical question that's gained startling traction among scientists and tech billionaires alike. And while it sounds like the plot of a sci-fi movie, the arguments behind it are eerily compelling. Start with the math. If civilizations inevitably develop the ability to create hyper-realistic simulations, one so detailed their digital inhabitants believe they're conscious, then the sheer number of simulated realities would dwarf the one base universe. Think of it like video games. Right now, billions of people play open-world games where non-player characters follow scripted routines. Now imagine a civilization a million years more advanced than ours. Their simulations wouldn't just mimic reality, they'd be reality to those inside them. Statistically, the odds that we're the original, non-simulated beings shrink to near zero. Then there are the glitches, oddities in physics that feel like bugs in the cosmic code. Ever experienced déjà vu, that uncanny feeling you've lived a moment before? Some jokingly call it a memory reloading error. More seriously, look at quantum mechanics, particles existing in multiple states until observed. It's almost as if the universe is optimizing processing power by only rendering details when needed, like a video game reducing graphics quality in areas the player isn't viewing. Even the speed of light, the universe's ultimate speed limit, could be seen as a hardware constraint, the processor's clock speed preventing the simulation from crashing. But not everyone's convinced. Physicists like Sabine Hossenfelder argue the hypothesis is unfalsifiable, it can't be tested, so it's not science, just metaphysics. Others point out that simulating every particle in a universe would require more energy than the universe itself contains, making it absurdly impractical. Unless, of course, the simulation isn't rendering everything at once, maybe it's using shortcuts, approximating the unseen just well enough to fool us. The darkest twist: if we are in a simulation, there's no guarantee the creators want us to find out. Would they let their experiment unravel if we cracked the code? Or would they hit delete and start over? Maybe ignorance isn't just bliss, it's survival. Either way, the simulation hypothesis isn't just a wild thought experiment. It's a mirror, forcing us to confront how little we truly understand about the nature of reality, and that's a mystery no amount of processing power can solve for us. From the Great Attractor's invisible pull to the eerie whispers of the wow signal, from the ghostly absence of dark matter in certain galaxies to the cosmic hexagon spinning above Saturn, each of these 25 mysteries isn't just a puzzle waiting to be solved. They're signposts pointing toward the next frontier of human understanding. Think about it, every time we've stared into the void and asked why, we've uncovered not just answers, but entirely new questions that reshaped science itself. The hunt for dark matter forced us to question the very fabric of gravity. The enigma of Mars methane keeps us guessing about life beyond Earth, and the simulation hypothesis. It challenges us to redefine reality itself. These aren't just curiosities, they're catalysts. Every unexplained flicker of a distant star, every anomaly in the cosmic microwave background, every bizarre object defying classification pushes telescopes to peer deeper, computers to simulate more precisely, and minds to stay open to possibilities we haven't even imagined yet. That's the beauty of cosmic mysteries. They don't just test our knowledge, they test our creativity, our patience, and our willingness to admit how much we don't know. So now it's your turn. Which of these 25 cosmic riddles keeps you up at night? Is it the haunting silence of the Fermi Paradox, or the way Oumuamua taunted us with its impossible shape? Maybe it's the quantum foam, where spacetime itself might be seething with chaos we can't yet see. Drop your favorite in the comments. Let's geek out over the universe's greatest unsolved cases together. And if you're craving more deep dives into the weird, wild corners of space, hit subscribe, because the cosmos, it's got endless secrets left to spill, and we're just getting started.